I'll finish off the last theorem of this chapter, of this lecture, which is asking the question whether there's a bijection from these fibres to these points. What's a fibre again? It's an equivalence class, right? All the little x's, all the members of this set X here, that in this Venn diagram, that belong to this subset, they all map to the same point, the same f of x, f of little x. Okay? So in this band, if you like, or fibre as it's called, all the members, little x, of this set big X, all of them in this band, in this subset, they all map to the same point here. So you have here like three equivalence classes, or three fibres. And just by looking at the diagram, you begin to suspect, well, maybe there's a bijection between a fibre and the point. So in terms of sets, a bijection between the set of fibres and the set of these points. And the set of these points is just called the image of f. F is your function that maps your little x into these points. Right? So the suspicion is, the hypothesis is, that you've got a bijection between the set of fibres and this set, the image of f. These points that each fibre gets mapped to. Right? So you just have a general function f that maps from x to y. So this is your x. This is just an arbitrary a set y, and an equivalence relation is defined if f maps. So for A and B belong to big X. They're just two arbitrary members. Okay, so this equivalence relation is defined as if for two random elements of X, if f of A equals f of B. Right? Now we suspect that there's a mapping between. Now, what is this? A strange symbol. Don't worry about it. For a moment, just think of it as a label. But it will take on meaning in later lectures. So just sort of get used to it for a little while. Especially this like division sign. So you're probably getting suspicious. It has something to do with factor groups or quotient groups, and you would be right. But we have to wait another till the last lecture, lecture 19, before the significance of this division takes on meaning. But for the moment, just think of it as a label, right? And what does it mean? Well, it's just a set of fibres, right? So these fibres, these equivalence classes, right? So it's just the set of them. And so call that set of the fibres this, right? And the conjecture is this function maps this set into and maps bijectively. That's the theorem that we'll try to prove. We'll try to prove that this mapping that maps this set of fibres into the image of f. That's the set of these points that each of these fibres or equivalence classes maps into. Right? That set. Okay. Now that's thinking in terms of mapping set to set. How about mapping element to element? Because that's the critical assertion. The critical part of your proposed proof is choosing an appropriate mapping. Well, what are the members of this? Well, they're equivalence classes. So of this form, right? X bar. That's just the equivalence class. All those members that are equivalent to a little element little x. Okay? And the members of this, what are they? Well, they're just f of x's. Okay? Remember, f just maps x, little x, one of the members of this set into some point, which is a member of this set, which is just f of x. Okay, so that's the form that this function will map an equivalence class into f of x, some member of this set, the image of f, right? And the assertion is, the theorem statement is that this function is bijective. Okay, so let's prove it. Well, as usual, firstly, is it well formed? Before we get on to injective and surjective, to prove bijection, firstly, is it well formed? Does it make sense? Like, say, we have another point y in this set. Well, if we have another member in this set, remember this is the set of fivers, and a fiver is just an equivalence class. Now, and if they're equal, if the equivalence class x and the equivalence class y are equal, right? If this is well defined, will we get sigma of x bar equal to sigma, or theta of x bar equal to theta of y bar? Is it well defined? Right. Well, so if these two equivalence classes, two fibers, are equal, then from theorem 55, go back two theorems, then theorem 55 says if that's true, then this is true, that that x and y are equivalent. Right. This theorem, I think, was it both ways? I need to check. 55. Was it? Yes, it was both ways, if and only if. 55 part 2. A is equivalent to B if and only if A bar equals B bar. Right, well, now we're talking about x and y's. Right? So we've got that's true. But what does this mean? Well, it means f of x is f of y. Right? From here. That's how this thing is defined. So if that's true, then this is true. Now, if that's true, then this is true from this. Okay. So if f of x equals y, f of y, then this equals this. Okay. So we've shown that it's well formed. Now, how about injective? Now, well, proof fairly standard. The usual technique for showing a function is injective. You take two points here. You assume they're the same, and you try to deduce that the point. Oh, this one maps to that, and this one maps to that. Now, if these two are the same, if it's injective, you have then these two will be the same. Okay. We've done that many times now. So assume this equals that, and see if we can show that these two equivalence classes are just the same. In other words, x bar equals y bar. Right. So let these two be the same, and we have to show that x bar equals y bar. Now, if this equals this, then from here we know that f of x equals f of y. But that means that x and y are equivalent, right? That's how we define this, was by this. Okay. Now again, by theorem 55, if x is equivalent to y, therefore x bar equals y bar. This equivalence class is the same as that one. All right. So we've shown it. That's what we show. So we've shown that it's injective. This function theta is injective. All right. Now let's try to show that it's surjective. And what does that mean? If a function is surjective, that means every element in your target set is mapped to. There are no stragglers. There are no what's the word? There are no isolated members that are not mapped to. They're all mapped to. If you have if your function is surjective. All right. Okay, so for every element in your target set, call it y, it's just an arbitrary element, y, there will be some member in x, little x, call some, that is mapped from into y, okay, because of this. That's what y is. And this set here, what is it? Well, it's the image of f. It contains all the elements that are mapped to. So it's virtually surjective by definition. Anyway, so given this y, there'll be an x that maps to it. Now we're talking about equivalence classes. Now, for a given x, any member of the big set x, your starting set, there will be a corresponding equivalence class x bar. Right? This x bar is a subset of all those members that are equivalent to this member little x. Right? So you've got this equivalence class here, this fiber, right? X bar. So for